Hello everyone, this is week 5 of our Intelligent Agents and Learning Environments course. We're going to continue learning about transformers by going more in depth about the attention block. Today, we're going to be covering attention in transformers, memory in large language models, and what induction heads are. First, we're going to continue talking about the attention block in transformers. As we previously learned, the attention block allows vectors to communicate with one another to determine the meaning of the word based on the context in which it is used in. Based on the context, the attention block assigns different weights or scores to the vectors assigned to each word. Each word has an initial vector embedding, which determines the meaning of the word used in the current sequence. As covered last week, the three main components of the attention block are the query, key, and value. The query refers to the general topic that you are looking for. It can also be seen as a request for information to further understand the context of the word. The key is a piece of information that is compared with the query to see if it matches what you are looking for. It measures how relevant it is, and it may also be a description of the query itself. The value is the actual information that is taken based on how relevant it is to your query. There are many different operations occurring in the attention block, such as the attention pattern. The attention pattern determines which tokens are important to update the meanings of other tokens. The model looks at the relationships between tokens and decides which ones should be focused on to have a better prediction of the next token that should appear in the sequence. The weighted sum is when each vector is multiplied by the weights received from the attention pattern, and then all the values are summed up together to have a refined embedding of the word. Multi-headed attention is another topic that we covered last week, and it is when multiple attention heads are used to simultaneously focus on multiple vector relationships. Each attention head produces its own context embedding, which is then added up to have a final contextual sum of the current word. Lastly, masking certain words prevents them from influencing the meanings of other words in that sequence that the current word is not relevant to. Next, we're going to talk about memory in large language models. As we previously learned, these models use a transformer architecture, and inside the multi-layer perceptron layer, also known as the MLP, vectors go through a series of operations. This process happens in parallel to every vector token that passes through that layer. As the vector goes through that layer, it goes through multiple mathematical operations. The first operation is the up projection. It takes the input vector and multiplies it by a large matrix, which is like a set of questions that the vector is asked, and the product vector is then added to the input vector, and the sum of those two vectors will be the final result. That result is then passed through the next operation, which is the ReLU operation. It is a nonlinear function that converts negative values to 0, allowing the machine to create better distinctions between vectors. The vector is once again multiplied by another large matrix for the down projection operation to reduce the vector's dimensions. We can look at each column of the matrix as a direction in a three-dimensional plane, x, y, and z. It is added once again to another bias vector, and the last operation, the residual connection operation, finally adds the result to the original input vector. All previous and future facts and information will be stored in the multi-layer perceptron layer. As vectors pass through the multiple MLP layers, the machine collects more information and context and stores it to make better predictions about which token comes next based on what it already knows from previous encoded information and relationships. Scientists created a hypothesis that LLMs do not represent clean one-to-one features, but rather combinations of multiple features. They believe that neurons can represent more than one feature simultaneously, and this allows the machine to store even more information by using nearly perpendicular values in a three-dimensional plane, like 89 to 91 degrees, rather than an exact perpendicular value like 90 degrees. Since a singular neuron can represent more than one feature, it makes it difficult to interpret singular ideas. So instead of one neuron activation corresponding to one idea, it would instead take a combination of multiple neuron activations to represent a singular idea. Lastly, we're going to be talking about induction heads. Induction heads are attention mechanisms that learn to detect and complete repeated patterns in a text. When a token appears twice in the same sequence, the induction head remembers what comes after the first instance and uses that information to predict what might come after the second instance of that token. It does this by performing two operations. First, the previous attention head looks backwards to find the first occurrence of the current token, and then the next attention head looks at what comes after it. It involves the use of query vectors to look back into the sequence and search for matching tokens. Then, it uses value vectors to relay the information forward and encode information about what follows each token. When a match is found, the head can use the stored next token information to make its predictions. Thank you for watching.